Hello guys, welcome to this video. Here I'm going to show you why the sample variance is an unbiased estimator. So remember that the sample variance is defined like this. So the question is why we divide over n minus 1 and why we don't divide over n. So we need to compute the expected value of s squared, which is just the expected value of all this. Sum over I xi minus x bar squared. So since we're going to be using a lot of this kind of sums, I'm just going to save some time but not writing everything like this, I equals 1 and n, and just here just I. We're going to sum, we're going to add over all i's. So the first thing that we're going to do is this is a constant, so we're going to take it out of the expected value, and this expression squared, we're going to expand it. So in our first step we're going to have 1 over n minus 1 expected value of the sum of xi squared minus 2xi plus x bar squared. So now we have this sum of these terms, but we can split this sum into 3 sums. Let me show you how to split it. The expected value of the sum of xi squared minus this plus sum of x bar squared. So we took out 2 and x bar because 2 is a constant and x bar doesn't have the index I. So we take those 2 out of the sum. So the same thing is going to happen with x bar squared. X bar squared doesn't have the index I. But what happens if we add n times this? Well, we're going to have something like this. Let me move this a little bit up. So we're going to have n minus 1 expected value xi squared plus n times x bar squared. This is what we're going to have. So now we need to consider the following. X bar, which is just the sample mean, is computed like this. So this means that if we take this n and move it to the other side, then we're going to have the following expression, n x bar. So what we are going to do is we're going to take this sum of xi's and substitute it with this. So we're going to have the following expression, 1 over n minus 1. Everything else remains the same. Nx bar plus nx bar squared. So of course here we have x bar multiplying x bar, so we can simplify. To nx bar squared plus nx bar squared. So you notice that we can simplify these 2 terms, right? Both are nx bar squared. This is a minus 2, this is a plus 1. So we can simplify like this. Minus nx bar squared. Excellent. So now, guys, we have the expected value of a sum. Well, it's a difference. But we know that the expected value of a sum is the sum of expected values. So let's work in that sense. This is 1 over n minus 1 times the expected value of the sum minus expected value, sorry, let me write this again, and x bar squared. So here we're going to use again properties of the expected value. Here we have the expected value of a sum, so this will become the sum of expected values. We're going to switch places between the expected value and the sum, and here n is a constant, so we're going to take it out of the expected value. So we're going to have something like this: sum of the expected values of xi squared minus n times the expected value of x bar squared. Excellent. So now we're almost done. Let me highlight this with blue, and let me highlight this with green. So for the blue piece, remember that the variance of a random variable is just the expected value of x squared minus the square root of the expected value. So if we solve for the expected value of x squared, we're going to have the following expression. Right? We're just going to take this term and move it to the other side. And this is what we're going to have. But we have a sum of expected values of a random variable squared. So what we can do is the following: the sum of the expected values is going to be the sum of the variance of the expected values of the random variable, sorry, plus the expected values squared. So now take a look at this. The variance of each of these random variables is going to be the same. What do I mean? Suppose that each xi has a normal distribution. It doesn't have to, but just for simplicity, imagine that x1, x2, x3, and so on, they all have normal distributions. So the variance of these random variables are going to be sigma squared. And the expected values, all of them are going to be mu's, but they are squared, so we're going to have this. So sigma squared and mu are not dependent on the index I. So we're going to add n times this constant. So we're going to have n times sigma squared plus mu squared. Right? Now for the green piece, we're going to work almost in the exact same way. The expected value of x bar squared is going to be the variance of x bar plus the expected value of x bar squared. So now what we're going to do is we're going to substitute x bar with this. Remember, x bar is just the sample mean, and the sample mean is computed like this. And now the expected value of x bar is just mu. How do we know? Remember that x bar is an unbiased estimator of the population mean. The population mean is mu. And if it's unbiased, that means that the expected value of the estimator is going to be the same as the parameter that we are trying to estimate. So this is going to be mu squared. Now we're going to exploit the properties of the variance. And 1 over n is a constant. So the way to take out constants out of the variance is by squaring them. So we're going to have this, the variance of the sum of xi over I plus mu squared. So the variance of a sum is the sum of variances. So again, the variance of each xi is going to be sigma squared. So we're going to sum n times sigma squared. So this is what we're going to have. N times sigma squared, because the variance of the sum is the sum of the variances, plus mu squared. Of course, we can simplify. Here we have an n, here we have n squared. So we can write this as 1 over n sigma squared plus mu squared. So now what we're going to do is we're going to substitute this expression and this expression here and here in matching colors, obviously. So what we're going to have is the following. So let me copy this and move it down here. So we have the three expressions at the same time. So let me arrange this a little bit. Okay. So now the blue part, 1 over n minus 1, times is just going to be n times sigma squared plus mu squared. This minus, be careful, this minus is this minus. Now we have an n. This n is multiplying the green expression. But if we multiply the green expression by n, this 1 over n is going to become 1. So we're going to have minus sigma squared minus n mu squared. Let us move this a little bit up. Now let's take away these parentheses. 1 over n minus 1 n sigma squared plus n mu squared minus mu squared minus n mu squared. So we can simplify n mu squared, positive, negative, they cancel each other. So this is 1 over n minus 1 n sigma squared minus sigma squared. So now we can factor sigma squared. So this is going to be 1 over n minus 1 times sigma squared n minus 1. And of course, this n minus 1 cancels with this n minus 1. And we are done. So this is one way to prove that the sample variance, let's recall all the procedure that we done. The expected value of our sample variance following this path results in the population variance. So this proves, so the expected value of the sample variance is just the population variance, thus is unbiased. So that's it, guys. Thank you. See you in class.